This is part 2 of the series Logarithmic, Exponential, and Other Transcendental Functions. And you might remember from the last video that we looked at the definition of the logarithmic function, and we saw that the antiderivative of the reciprocal function 1 over x was the logarithmic function, and that's where the definition comes from. And we discovered that using several of the basic logarithmic properties. So we're going to start this video by looking at where those logarithmic properties come from. So here we have 4 basic logarithmic properties. The first property, the natural log of 1 equals 0, is a direct consequence of the definition of natural log. And we can see here that the definition is natural log is the definite integral from 1 to x of 1 over t dt. Now, if we just assume for the sake of discussion that x is 1, then what we're doing is taking the area of a curve that has a width of 0. So if the width is 0, the area under that curve naturally has to be 0. So that's where the natural log of 1 equals 0 comes from. Now let's go ahead and look at the second property. Here the property states that the natural log of some value of a times b is equal to the natural log of a plus the natural log of b. Now, in order to determine where this comes from, what we're going to do is consider the derivatives of both sides of this equation. Let's go ahead and take this one piece at a time. The left side is natural log of a times some value x, and the derivative of that, the derivative of ln of ax, is 1 over ax times the derivative of ax. So the derivative of ln of ax is 1 over ax, and the derivative of ax is just a. Clearly the a's cancel out, and we have this derivative as 1 over x. Now if we consider the derivative of the right side, ln of a plus the ln of x, we get this. And since ln of a being a constant, is just a constant, the derivative of a constant is 0. And when we have the natural log of x, it's the derivative of ln of x is 1 over x times the derivative of x, which is just 1. So again we have the derivative of ln of ax is equal to the derivative of ln of a plus the ln of x here, 1 over x. That means that 1 over x is the antiderivative of both ln of ax and ln of a plus the ln of x. Now what that means, if you recall from the definition of antiderivatives, is that these two expressions are exactly the same except for the constant of integration. So the ln of ax equals the ln of a plus the ln of x plus some constant of integration c. Now, just for the sake of the proof, if we let x equal to 1, we have ln of ax and x is 1, that gives us ln of a. And then if this ln of x, if this x is 1, then ln of a plus ln of 1 is ln of a plus 0 plus c. And clearly what we have then, if we subtract out the ln of a from both sides, then c is equal to 0. Going back to this expression then, if c is 0, then ln of ax equals ln of a plus ln of x. So there is property 2. Now let's look at property 3. This is the ln of x to the n equals n times ln of x. So we've basically taken the exponent, pulled it out in front of the natural log. We're going to do something very similar in property 3 that we did in property 2. We're going to consider the derivatives of the left-hand side and the right-hand side. So let's go ahead and take a look here. Here is the property ln of x to the n equals n ln of x. The derivative of ln of x to the n is 1 over x to the n times the derivative of x to the n. And using the power rule, we have n x to the n minus 1. Now, here we have x to the n minus 1 divided by x to the n, And you can clearly see then that the n's are going to cancel out, and we're left with n times x to the negative 1, which of course is n over x. Now we'll go ahead and take a derivative of the right hand side, and we have n times ln of x, and the derivative of that using the constant multiple rule, pull out the n. That is 1 over x times the derivative of x, which was just 1, and again we have n over x. So here we see that n over x is an antiderivative of both n ln of x and ln of x to the n. So these two expressions must be identical except for the constant of integration here. So the ln of x to the n is equal to n ln of x plus c. Just like we did in property 2 here, we're going to let our x equal 1. So letting x equal 1, we have ln of 1 to the n, which ln of 1 is just 0. And we have n times ln of 1, which again is 0, plus c. So 0 equals 0 plus c, clearly c equals 0. And we're back to the same conclusion. We can see then that ln of x to the n is equal to ln of x, because the c here is 0. And that's property 3. Now let's go ahead and take a look at property 4. The proof of property 4 is just going to utilize a couple of the properties that we've just proven. Now first, let's look down here. We can rewrite the natural log of a divided by b using basic law of exponents. That's just the natural log of a times b to the negative 1 power. And this is a product, so we're going to use property 2, and we're going to say that the natural log of a plus the natural log of b to the negative 1 is equal to the natural log of a times b to the negative 1. And lastly then, we're just going to utilize the power rule here, and we're going to take that negative 1 and put it out front, and we have the natural log of a minus the natural log of b. So there's property 4. The natural log of a divided by b is equal to the natural log of a minus the natural log of b. Now the whole purpose behind our looking at logarithms in general and the properties of logarithms specifically is because logarithms are going to assist us in integrating and differentiating functions that would otherwise be a fairly major task. So let's take a look at how we're going to use logarithmic properties in our other functions. Now here we have 4 different expressions, and what I would recommend is that you start by pausing the video and see if you can go ahead and expand this logarithmic expression. And then go ahead and pick up the video and I'll work each one out in its turn. So if you go ahead and pause the video, and I'll start in a second. Now here in number 1, we have the natural log of a quotient. So we're going to use the quotient rule. The natural log of 10 divided by 9 is just the natural log of 10 minus the natural log of 9. Alright, so that was a pretty straightforward one. Let's now consider 2. Go ahead and pause the video, and I'll pick it up in a second. Alright, so this looks like we have a composite function here, and I'm going to rewrite this really quick. This is just the natural log of 3x plus 2 to the 1/2 power. Now here we have the power rule. So I'm going to pull out the power. And there's our expansion. Now this is just the natural log of a sum. We don't have any rule for that, so this is the expanded value. Alright, let's go ahead and consider expression 3. Pause the video, and I'll come back in a second. All right. Now this is another composite which has the quotient of a product divided by a constant. So first, I'm going to take the outside piece. We're going to have the natural log of 6x minus the natural log of 5. Now here we have a product, so I'm going to expand that. That's the natural log of 6 plus the natural log of x minus the natural log of 5. All right, fairly straightforward. Now let's finally consider expression 4. Go ahead and pause the video and see what you come up with. Okay. Now this is another composite function. So the first thing I'm going to do is I'm going to look at this quotient. Here we have the natural log of x squared plus 3 squared minus the denominator, the natural log of x times, now I'm going to expand this just to a rational exponent here. We have x squared plus 1 to the 1/3, and close that off. So that's the first piece. We're just using the quotient rule. Now in this one we have the power rule, so I'm going to pull the power out front. And then the next one, in this part we have a couple of pieces, so I'm going to separate it out with a bracket. And we have the natural log of x times this piece. So that's going to be plus the natural log of x squared plus 1 to the 1/3. And then in the next line, we're going to expand this guy. So we're just going to copy this thing down. Now here, we're going to pull out the 1/3. And we have ln of this inner piece. Now finally, we'll distribute out that negative sign. And there we have it. Now before we move on, consider if you were asked to differentiate this expression. Clearly, that would be very, very difficult with the experience we have so far. But if you take a look at differentiating this expression, you can see that it would be relatively simple, and we wouldn't have a whole lot of work to do. So that's the whole reason behind doing these logarithmic properties and doing this expansion. It's going to be allowing us to take a look at the derivative and, in many cases, the integral of a more complex function and treat it as a grouping of simpler functions. All right, well, I'm going to go ahead and end this video, and we're going to begin the next video by taking a look at the natural number e. So I will talk to you in the next video.